Well, today we are obviously continuing on GD&T. So far we've done straightness and we've done flatness. Today we're going to talk about straightness of a feature size. So I'll explain the difference of straightness and straightness of a feature size in just a moment. Before I do, I want to talk about some of these modifiers that we'll begin to see this chapter, or this section I should say. We've talked before about maximum material condition and least material condition. So if I'm talking about an external feature like a cylindrical shape, the maximum material condition, or the MMC, is when there's the most material. So the biggest cylinder, for example, out of the tolerances. And if I'm talking about an internal feature, then it's the smallest hole. So the smaller the hole, the more material there is. So we'll be referring to the MMC inside of some of our feature control frames today. We can also see the LMC for least material condition. So again, the smallest external part, or the largest internal hole, which will leave the least material afterwards. And then we also have regardless of feature size. So you'll see RFS sometimes for regardless of feature size. So that means really it doesn't matter if it's MMC or LMC or anywhere in between. We're going to apply the tolerance the same no matter what. Now the S is an older symbol. The ANSI standard has changed, and pretty much if there's not an M symbol and there's not an L symbol, then by definition it's regardless of feature size. But I always like to show the S because you might run into some old drawings at some point and wonder what it is. But basically, if there's no symbol, it's regardless of feature size. So the big difference between straightness and straightness of a feature is how we apply it, first of all, to the drawing. So when we were talking about the straightness of a surface, or straightness, of a cross-section of a line, we pointed to the surface. So we had a leader and we pointed to the top surface, for example. When we're talking about a feature, we're actually going to apply it to the dimension itself. So no leader, you just tuck it underneath the dimension itself. So this is saying that we've got a diameter between 1.5 and 1.506, and it has a straightness value of 0.002. Notice the diameter symbol. That's new for us. The diameter symbol comes because of the shape of the tolerance zone. So I'm going to switch to Inventor and try to show you this visibly here. So here's my cylinder, and as you can see, it's got the axis running through it. I'm going to show shaded with hidden edges so you can see inside this part. So there is my axis. So when we have talked about a straightness of an edge, so if I put in my leader and I pointed to the top edge and I said it had a straightness value of, say, 0.002, then basically what I'm saying is that I've got a tolerance zone of the 0.002 where that edge could lie on. But instead of doing that, we are now applying it to the dimension. When you apply it to the dimension, what you're actually doing is applying it to the axis. So no longer am I saying it's the straightness of the edge out here. I'm talking about the straightness of the axis itself. And when we look at it maybe from this front view, I would have a tolerance zone that looks something like that. So here's my original axis. It can vary up above or it can vary up below. As long as the axis lies between these two lines, it's still a good part. Make sense so far? It's really what we talked about last couple class periods, but just doing it to the axis now. But the thing about the axis is it's, I can rotate it and look at it from different directions. So what if I look at it from the top? So since I'm applying it to the axis, well then that also means as I look down from the top, I'm going to have the same tolerancing. It can vary inside this area. And truthfully, I can look at it from any number of angles. So what I end up with is a circular tolerance zone, because that axis can lie anywhere within that range. So because I end up with a circular tolerance zone, that's why we put the diameter symbol in there. So if you're applying it to a cylindrical shape, you're applying it to the axis, and the resulting shape is a cylindrical tolerance zone that axis can vary within. And thus we put in the diameter symbol. So that's why the diameter symbol is there. Again, trying to show it in a 2D view. Same idea. I've got the circular tolerance zone here, and you can see above and below, but I think you could picture it in the 3D mode a little better, which is why I pulled that up. So if I'm looking at straightness of a feature size, perfect form at MMC is no longer required. So that's only when we're pointing to an edge. But when we attach it to a dimension, that rule is out. So if we read this tolerance out, we're saying this has a straightness applied to the axis, which has a diametrical shape of 0.002 regardless of feature size, right? So if there's no M and there's no L symbol, it's regardless of feature size. So what should the tolerance be if it's 1.506? 0.002. What should it be if it's 0.505? 0.002. So when we say regardless of feature size, it's going to hold that tolerance all the time. So then we're going to throw in some maximum material condition here. So if I look at the first one, we're going to first talk about virtual condition and then apply the MMC to it. So virtual condition is where I'm basically looking at the MMC of the part. So if I have just the cylindrical shape itself, and I ignore this tolerance, and I look at the upper and lower values, the largest this shape can be, the MMC of the part, is 0.5. Would you agree? So it would be 0.5 plus 0 minus 0.006, but for the maximum it would be 0.5. And then I'll add to that the feature control frame tolerance of 003. And that means that the virtual condition, the largest this area could be, is going to be 0.503. That's my virtual condition. So you're going to add your MMC of your dimension part plus the feature control frame. So the virtual condition, what that means is if I have the dimension here of 0.003 applied to the axis, and this axis is able to vary within that cylindrical range, then as a result, the part could actually end up being larger than 0.5. Now, any given moment on this part, if you measured it, it would be the 0.5, but because it flexes, it can have a virtual condition of 0.503. So that's a little hard to wrap our heads around. Is that making sense, what I'm saying there? So the part itself is still 0.5 thick, but because it can flex and still be in that allowable range, we get a virtual condition of 0.503. If it's an internal feature, then we're going to subtract. So the MMC is the lower value now. So if I have 0.5 plus 0.005 minus 0.000, so my maximum material condition is going to be the smallest whole, since that gives me the most material. And then I'll subtract from that the 0.003. So my virtual condition is 0.497. So if we look at this one, the hole at any given point is 0.5 across, but because of the allowable flex of the axis, I can only fit a straight pin of a diameter of 0.497 through here because of the curve of the hole shape. So again, external feature, we add the MMC and the feature control frame for the virtual condition. Internal feature, and then we're going to take the MMC and subtract the feature control frame. So here's an exterior feature. Now notice the MMC modifiers added on there. We'll talk more about that in just a second. But just looking at the virtual condition, I'm going to look at the MMC of 1.506. I'm going to add the 0.002, and that will give me a virtual condition of 1.508. Internal feature, again, smallest value is my MMC, so that's 1.5. I'll subtract from that my feature control frame tolerance, and my virtual condition is 1.498. So far, so good? Okay, so now I have the MMC modifier in here. And this is going to give us what we call a bonus geometric tolerance when we apply it to a feature size. But what we're saying, again, if I were to read this out, I'm saying that this needs to have a straightness tolerance with a diametrical shape of 0.002 at the maximum material condition. So that means when it's at 1.506, this is going to be the tolerance value. So let's break this down a little bit here as we compare having the MMC modifier and not having it. So first of all, not having it. I've got a cylindrical shape here, and it has a limit dimension of 0.615 down to 0.605. And then it also has a straightness tolerance applied to the feature, yeah, that's right, of 0.015. So what would my tolerance be? Well, I don't have the MMC modifier, so it's regardless of feature size. So no matter what, it's going to be 0.015 for my tolerance zone. And if I look at that actually applied to the part, so the virtual condition, again, is going to be the largest part, most material, 0.615, plus the feature control frame tolerance for 0.630. So my virtual condition is 0.630. My axis through here can vary anywhere within that 0.015 tolerance zone. And again, the part ends up being the 0.615, the maximum, but because of the allowed variance in the axis, the part can curve, and then I have my virtual condition here. So we're stuck on 0.015 regardless of feature size. When we look at it with the MMC modifier, so same exact part, but I've got the MMC modifier now. So what that is saying then is that it is going to be 0.015 at the maximum material condition. So if I jump down to this table, at 0.615, its tolerance is 0.015. So that's what we're saying there. Then as the part gets smaller, then I've got a larger tolerance zone, just like we talked about before when we were looking at straightness and flatness. So as the part continues to get smaller, it can get larger. But as you can see in this table, we can actually have a tolerance zone all the way up to 0.025, which exceeds this 0.015, right? And it also exceeds the 0.15 in here. So this is where the bonus tolerance comes in. So let's look at these images over here on the right. So first of all, I've got a cylinder with the MMC diameter of 0.615, and I'm putting it into a gauge to test the cylinder is what I'm doing here. So the gauge has a diameter of 0.630. The virtual condition fits in there just fine. So if I look at it with the maximum material condition when it's 0.615, and it can have a variance of 0.015, it fits within this gauge. So just like we've looked at so far. But when I throw the MMC in there, the issue is it's 0.615 at it's 0.015 at MMC, but as this cylinder gets smaller, then we have more variance in there. And if I choose the smallest cylinder of 0.605, it can still fit inside this 0.63 virtual condition gauge with a variance of 0.025 applied to the axis. So the thinner that part gets, the more it can flex and still fit inside this gauge. And again, we can do that because we have the maximum material condition applied. When we don't have that, it's got to be 0.015 regardless. We can't have this bonus tolerance applied to it. So again, going back here, it's always got to be 0.015. But as soon as I put in that MMC modifier, then I'm saying it's 0.015 at MMC, but it's going to expand as it gets smaller. And then we get our bonus tolerance. So seeing it here again in some additional slides, this one with the MMC modifier, if I've got the virtual condition, which again is going to be the MMC of 1.506 plus the control frame tolerance of 1.508. So I'm going to take the virtual condition minus the size here. So at MMC, I've got a tolerance of 0.002. But again, as the part gets a little smaller, then I've got larger tolerance, and it will just continue until I get to the least material condition, which again is going to be basically the tolerance then is the actual value tolerance here plus the feature control frame is my total tolerance. Question, Gabe?
If the size goes up or down 1,000, the tolerance goes up 1,000?
Yes.
Would it change if, like, let's say the size went down 100? Would it go down? Would it go up 100?
Yes. So yeah, I would just keep the same ratio. So whatever the part gets smaller, then the tolerance goes up that same amount. Now it is possible, we'll see an exercise in just a little bit I don't have a slide for it, unfortunately, but on one of the exercises, and it's in the book as well, you can also have a max tolerance value out here. So in addition, in the control frame, it might say max 0.004. And so in that case, once I got to 4, then I would just repeat the 4. And that would basically eliminate that bonus tolerance and keep it from bending as much maybe as I want it to. So again, regardless of feature size, I read that and I see, okay, this has a straightness tolerance of 0.002 regardless of feature size. So literally, regardless of what size it is, that's 0.002. It's got to stay in that range. But again, as soon as I throw in that MMC modifier, then I'm going to have the bonus tolerance situation. So I'm going to take my virtual condition. So in this case, since it's an internal feature, it's going to be the smallest hole minus the control frame tolerance. So that'll give me a virtual condition of 1.498. And then I'll just subtract the difference between them. So when it's at the smallest hole, I've got the tolerance of 0.002, which again is what this says. At MMC, it's 0.002. Then as the hole gets larger, and I subtract the size of the hole and the virtual condition, then I'll get the difference there. And that's why, to answer your question another way, Keith, you're always taking the actual size of the part and subtracting the virtual condition. So the virtual condition changes. So if the part changes by 100th or 1/10, then as I subtract, the tolerance will change that amount as well. So again, as I continue all the way up to the least material condition, that tolerance is the total tolerance of the feature itself plus the control frame tolerance. So it's allowed to vary a little bit more with that bonus tolerance. So in this case, I've actually got 0 tolerance at MMC. To help control it a little better, I'm going to say when it's at maximum material condition, it can't vary. It's 0 tolerance at MMC. So if I'm looking at virtual condition, the virtual condition is the smallest size in this case because that's MMC minus the control frame tolerance. So my virtual condition is just simply 1.5 then. So 1.5 minus 1.5 is obviously 0. And then as I continue each time subtracting from 1.5, then I'll have my geometric tolerance of 0.06 is the max that can be. But this way I'm holding it at the maximum size to 0.00. So here's another example, this time applied to an external feature. So straightness tolerance of 0 at MMC. So MMC is going to be 1.506. So I've got no tolerance there, 1.506. And then again, as the part gets smaller, then I'm going to have an allowable tolerance where that center axis is allowed to vary, but no more than the actual part tolerance. So before we look at the exercises, is this making some sense? I know there's throwing a lot of stuff at you. Let's look at the exercises you're going to do today. So there's actually 6 of them. Some of them are fairly easy. So these are all in the 4 folder. I forget exactly how I've got it named, so let me do a new here if it'll let me. Please don't crash. There we go. Okay, so these are in the 16-4 folder, all 6 of these exercises. So let me kind of run you through each of these. The first one, quite simply, you are to calculate the virtual condition. So MMC or not, doesn't matter. Again, same rules. We want to take the MMC of the part and then either add the feature control frame tolerance if it's an external feature or subtract it if it's an internal feature. So all you got to do is double click answer and replace it with your actual value answer there. So just 4 little answers there. The second one, this one, just thinking a little more about this one, it says the hole does not have a straightness tolerance. What is the maximum permissible deviation from straightness if perfect form at the maximum material size is required? Double click the answer and supply your answer. So if you don't have a straightness tolerance value, what tolerance value do you use? What's that, Keith?
0.
We use the part tolerance. So this is just kind of a reminder that if you don't have a straightness tolerance value, then we're using the part tolerance value. So what is my tolerance of this feature?
0.003.
Exactly. So that one's pretty easy. But just want to remind you, again, the differences between whether or not we have the control frames. So for this particular one, we've got an external feature, and we've got an MMC modifier, and it's attached to the dimension. So the virtual condition of this one, again, is going to be the MMC plus the feature control frame tolerance. So you'll be able to edit that value there to change that. And then it's just simply a matter of subtracting your virtual condition and the tolerance value to get that answer. So if my MMC is 1.994 and my tolerance is 0.002, then my virtual condition is?
0.996.
Yep, just those two values added together, 1.996. So then 1.996 minus 0.994 is going to be 0.002, 0.003, and so on. But this is where we'll get that bonus tolerance. So the tolerance is going to be the 6 thousandths plus the 2 thousandths of the control frame. So I'll have a total tolerance of 8 thousandths there. Okay. Next one. This time we've got a max value on there. So, and it's a metric one, but we can do the same thing. So we have a tolerance of 0 at MMC. So 15.9 is our MMC, and this is our tolerance. So our virtual condition is those two values added together, or just 15.9. So when I take 15.9 and subtract it from 15.9, I get 0, which is what it says, 0 at MMC. And then it will continue as the part gets smaller, the tolerance will increase the same amount, but eventually we'll reach the max of 0.4, and we can't go beyond that.
So you just keep putting 0.4 down?
Yep, you just keep putting 0.4. It can't exceed that. Good question. Internal feature, same kind of thing. Don't have a max this time, but again, remember that virtual condition now is the MMC, which is the smaller number, minus the control frame tolerance. So 1.242 for my virtual condition, and then again, just simple subtraction. I don't have a max, so I'll just keep going until I get to the overall bonus tolerance, again, of 6 thousandths plus 2 thousandths, or 8 thousandths. And then finally, the last one here. What is the maximum deviation permitted from straightness for the shaft if it was at MMC? So what is MMC for this shaft? 0.624?
0.625.
Well, not, yeah, just the shaft itself, yeah, not counting the feature control. So 0.624, that's the virtual condition. So good. So 0.624 is our maximum material condition. What is my tolerance at that value? Using the feature control frame. 0.001, okay. What's my LMC value, least material condition?
0.621.
0.621 is my least material condition. What is the straightness tolerance applied to the least material condition in this case? I'll give you a hint, you don't need to do any math. What's missing from this control frame?
Maybe 0.001 because it doesn't have the MMC thing.
That's right. So if it doesn't have the MMC, it's regardless of feature size. So it's 0.001 regardless of feature size. So any value in between 0.621 and 0.624, the straightness tolerance is going to be 0.001. My virtual condition is my MMC plus my tolerance. So that's what you were addressing, Keith, earlier.
Yeah.
So you really got to watch that MMC. That's what makes the difference, and that's why I threw this one in there. So again, you remember to look whether the MMC is there or not.
So what is the virtual condition in that case?
So the virtual condition, regardless of whether we have the MMC modifier or not, is always your maximum material condition. So in this case, it's the largest cylinder, plus your tolerance, straightness tolerance.
Okay.
So it would be your 0.624 plus your 0.001. So you always do that the same way. And it's kind of confusing, I know, because we refer to this as the MMC. It's the maximum material condition, but then we also talk about the MMC modifier as well. But it really doesn't matter if it has the modifier or not. You're still always taking the MMC plus or minus the straightness tolerance, depending on if it's an external or internal feature. All right, that's the plan for today. Again, on each of these, just put your initials as usual and print them out. If you have any questions while you're working on them, let me know.